It's my privilege to open the next technical talk by introducing Professor Abdullah P., an esteemed academic and accomplished researcher in signal processing and communications, who will chair this session. Currently a professor in the Department of Electronics at School of Engineering, Cochin University of Science and Technology, Professor Abdullah has a distinguished career in academia and research. His contributions include extensive work in speech processing, pattern recognition, and machine learning, significantly impacting these fields. Professor Abdullah has authored numerous research papers in prestigious journals and conferences, and his scholarly impact is evident from his citations on platforms like Google Scholar. He has also mentored several research scholars who now contribute to academia and industry alike. Beyond his academic achievements, Professor Abdullah has been actively involved in curriculum development and academic leadership at CUSAT. I now request Professor Abdullah to invite our esteemed speaker, Sri Ajith Peter. Sir, please.
Okay, we move on to the next session. We have Mr. Ajith Peter, is a director and co-founder of Asnaviram Networks Private Limited. And after completing his graduation, most of the education from Amrita Vishwavidya Peedam at Timur, and he did a junior research fellow at IIT Mumbai. And he has a lot of notable skills and contributions in the domain of RF, embedded system, high performance. Apart from that, as a co-founder and director of the company, he is consultant and visiting consultant in a lot of foreign countries like Sweden and almost all part of India. And I invite Mr. Ajith Peter to deliver his lecture. Thank you.
So, am I audible? Yeah. Okay. So, good morning. And so my topic basically is today software-defined radios in the industry. And I'd like to know, before I start, show of hands, how many of you are here undergraduates? UG? Okay. Postgraduates, I think the rest. I had prepared this talk with the later part of this talk, basically with more undergraduates in mind. So some of these might sound elementary to you, and also most of this talk has probably been covered in a couple of lectures which you had seen over the last couple of days. So there will be a lot of repetition in material, but I hope we can keep it interesting and relevant wherever possible. So the first part of my talk, basically I would like to visit the history of radios from spark gaps to cognition. So can anyone tell me what a spark gap is? Anyone? Spark gap was typically the first radio that came out, and predominantly was used in the time of Hertz, and it basically comprised of a make and break arrangement, typically a telegraphic key, which excited the energy across an induction coil and a capacitance, and there was some kind of a tuning resonance circuit, tank resonance circuit that was present, and the energy got coupled to an antenna and created a radiated communication scheme to begin with. Presumably this was the first time people started using make and break arrangements to modulate a continuous wave to communicate data and information across. Subsequently the radios evolved. My grandfather, who was a radio technician during World War II, basically used to work on these radios. They are essentially valve radios, vacuum tubes. And he came down, set up a radio shop in my native town in Palakkad, and started making and selling these broadcast radios. And in his time he was called Radio Marsh. He ran a training institute also, because people were interested in figuring out what was the magic that ran these radios in the beginning, and made a little bit of fortune in his time. But then in came the transistor, and lot more flexible, lot more smaller footprint, higher reliability, better fidelity, and my grandfather had to shut shop because there was no more novelty available and these systems could be churned out. My father spent his bulk of the career trying to work on televisions and the radio communication systems for law enforcement. And these are all conventional radios, the first and second generation radios. Essentially, the function defined the architecture, and presumably they carried out mostly one single function in a single radio framework. In our generation, we are looking at a sliver of silicon that one can hold in the palm of one's hand and has a multitude of radios. You have the cellular going all the way from the 2G spectrum, capable of handling the 5G spectrum. We have global positioning system constellations possible. There is Wi-Fi, there is Bluetooth, and there is even an FM radio, all being processed by a single chip. Okay, so considerable miniaturization has happened. And typically the conventional radio architecture had an antenna, some kind of an RF amplifier, a frequency translation device, usually a mixer coupled to a local oscillator, a bandpass filter, an IF amplifier, a functional demodulator that did one function, probably to demodulate audio or to video or any of those systems, and then there is an audio frequency amplifier followed by a loudspeaker. Okay, so one radio hardware for one dedicated function. In comes software-defined radio architecture. We have an antenna. Essentially, this chip, this entire front end, more or less remains the same, but is then abstracted to a single piece of silicon, and then out comes the intermediate frequency, which is digitized by an A to D converter, and then processed inside an embedded system, usually a DSP or an FPGA, right? So essentially, by changing the software that runs in your DSP or your FPGA, you can transform the function of the radio. So it's essentially one radio hardware and multiple applications as dictated by software, right? So we look at a broad, before we take a deeper dive, a brief idea into the evolution of hardware architectures in software-defined radios. So the first generation radios that came actually essentially operated with a sampling frequency of the A to D converters almost closer to baseband, right? So we have typically a bandwidth, system processing bandwidth of tens to hundreds of kilosamples per second. And the front end basically was heavy in the sense that the antenna was followed by a linear amplifier, image rejection filters, and then there was a large array of mixers and local oscillators that shifted your carrier frequency to an in-phase quadrature signal that could then be processed by an A to D converter operating at rates closer to the baseband, right? And then there was always a DSP that actually performed these computations at close to kilosamples per second and could decipher the information out, demodulate the information out. And these are typically some of those radios that came in that era. Typically what one calls a Taylor detector is a typical example, where you have a very simple antenna coupled with a simple circuit that you can fabricate with a series of operational amplifiers. This you can make, actually. There are a lot of kits that are available in the market, and you could attach the in-phase and quadrature outputs of these software-defined radios to your computer sound card, which is a decent A to D converter and a D to A converter built in onto your everyday computers, and even to your mobile phones also as well. There are softwares that are available, and you could tune yourselves to the HF radio transmissions and so on and so forth. And it's a brilliant toy project if you want to start tinkering with software-defined radios. The early architectures. Subsequently, what happened was A to D converters and D to A converters increased in speed and performance. The DSP processors also grew in speed and performance. Moore's law was having its effect, and therefore we started getting more miniaturized A to D converters capable of operating at tens of megasamples per second. And therefore what people could do was to transfer the high frequency carrier into some form of an intermediate frequency, have that sampled by a series of data converters, and then use locally programmable. So these mixers are essentially multipliers and numerically controlled oscillators that ran inside your DSP and could do bulk of the frequency translation and processing in the baseband inside the DSP. So the DSP starts getting popular and powerful. You can see that the right side rectangle starts encroaching into the analog hardware. And also The initial radio architectures that came were essentially, typically if you look at the hardware architecture of that system, it was essentially a 3-chip solution. So you had the antennas that could transduce the signal, take out the electromagnetic energy and then convert it to a voltage signal and have it coupled to some kind of an RF front-end chip, which did preamplification, frequency translation, and subsequently brought it down and then was sampled by some kind of an A to D converter and then fed to an FPGA, which acted as some kind of a data transport mechanism to a processor, which would then demodulate and run the algorithms and bring out the intelligence from the modulated waveform. So some of the early radios that came in this category essentially were the universal software radio peripherals. I think your laboratory has some of these radios with you. And there are different types depending on how the front ends are configured and how the interfaces to the processing platform is done. There are the network series, the bus series, and the embedded series that are available with this company called Hertz Research, which is now a part of National Instruments. There are also other radios that are available in the market. Adam Pluto is a notable low-cost alternative. There are also these radios like Lime SDR, Blade RF, Hack RF, and XTRX that is also available in the market. And the true democratization of software-defined radios, in my opinion, happened with the advent of this. This was a DVB dongle, digital video broadcast dongle, that became available from a Taiwanese company. Somebody hacked into its chip and was able to take out the in-phase and quarter-chip streams and was able to then couple it to popular software-defined radio platforms. And with $20, you could scan the entire landscape between somewhere around 100 megahertz all the way to 1.7 gig, and almost a large array of processing of the SDR of the radio communication spectrum would actually be captured and processed with this hardware. And this led to a lot of developments, a lot of open source, a lot of community building, and so on and so forth, and is still being actively used by a lot of hobbyists and professional practitioners alone. So if you look at the earlier USRPs that came, this is typically a USRP1. We had this radio with us in early 2005, and this particular radio essentially had a Cyclone FPGA from Altera that could communicate to a USB, and then there were 2 A to D converters onto which you could actually insert daughter boards, which would take the RF spectrum, amplify it, down convert it to baseband or IF, and then have it coupled to these A to D and D to A converters, and then they sample them, pass it on to the Altera FPGA, and then have it decoded on USB. So if you look at the main chip that ran on these, this was typically the kind of A to D and D to A converter architecture with a programmable gain amplifier, A to D converters, anti-aliasing filters, Hilbert filters, and so on, going into the baseband processing engine. So you can see that the primary element in these chipsets in the early days were essentially the A to D converters and the D to A converters, and some kind of an interpolation and decimation filters that actually used to match the sample rates for baseband processing. And these were the daughter boards that came out, which could be plugged into these slots, and they all operated in a specific frequency band, provided certain front-end bandwidths, and so on and so forth. And by changing these different cards into the lattice, we used to get different frequency coverages and so on and so forth. But it used to be painful, and the entire spectrum was limited to what each of these cards were able to process. Subsequently came the 2-chip solutions. So there the processor got absorbed into the FPGA. We started looking at system on chips like the analog devices, the AMD Xilinx Zinc system on chip, which essentially combines ARM Cortex processors on the FPGA lattice. So there was a miniaturization that was achieved there. And the front-end chips also evolved basically to pull in some of the key elements that actually form the RF front-end. And if you look at one of the ICs that came in this generation was the analog devices AD9361. And you could see that the front-end amplifiers, the low noise amplifiers, were integrated into the lattice. The mixers were integrated into the lattice. The local oscillators were also integrated into the lattice. So you feed RF in, it gets digitized, processed, and out comes IQ. that is the kind of miniaturization that happened in the 2-chip kind of solutions. And this is even actively used today in most of the applications. And some of the radios that came out were essentially these kinds of broadband radios. They could operate in a frequency entirely from 70 megahertz to 6 gigahertz with an instantaneous bandwidth of around 56 megahertz. And they were always coupled to some kind of a system on chip from AMD, and you can couple a series of RX and TX antennas to this side of the board, and out from this side will come IQ, or probably you could do a lot of processing inside the Zing SoC also as well to do a modem design or build most of the baseband processing inside this chip. Now, in today's age, probably a couple of years before, we are looking at nearly direct RF or all digital radios. And as you can see, this is more or less encroached completely into the analog front end part of the radio. You have an RF antenna that is coming in here. There is a minimal amplification and bandpass filtering that is done. And the A to D converter operates typically at sampling speeds of the order of a few tens of gigasamples per second, right? So what happens is you first sample the carrier direct, and then you pass it on to the lattice of the FPGA, from where you do numerical controlled oscillators, baseband conversion, baseband processing, and everything, right? So most of this, what you see here, is a single chip these days, right? And you will see that these are essentially forming what are called a single chip solution. So you give in RF energy directly into the chip, it gets sampled, digitized, processed, and demodulated all on a single chip. So this is typically one of the platforms that is out today. This is an RF system on chip. You feed in RF here, out comes a fiber. Okay, so all the signal acquisition, signal front-end processing, signal demodulation, intelligence extraction, everything happens inside the system on chip, and you just have a single wire. So all the complications of having multiples of RF circuitry designed and built is all gone, and all you require is to build minimal RF circuitry that is required to do preliminary acquisition, signal conditioning, and so on, and subsequently transfer that to fiber and therefore further processing. Some of the chips that we are having here typically have sampling speeds all the way up to 5 gigasamples per second, and some of the chips that are coming out from Intel has promised sample rates of around 64 gigasamples per second at around 10 bits. So that is the basic evolution that has happened in hardware. So we saw how multitudes of chips were used initially, and then it all came down, and we now have direct sampling receivers and direct sampling transmitters that can operate exactly, sample the electromagnetic spectrum first, and then do the rest of the processing. Okay, so a lot of evolution has happened in terms of hardware, and people are now looking into quantum radios, quantum processing, and so on and so forth. Quantum sensing, that sort of applications are also coming as a part of the new developments that are happening in the next generation radio front-end design. So now we will also take a brief look at typically what has been the evolution in software, and I'm sure most of these would have been covered in the previous days here. I'm just briefly trying to touch upon what are some of the key software platforms. If those of you are interested, could pick it up. So essentially, for the free and open source person, GNU Radio is a reasonably sophisticated, capable piece of software. Preliminary supported on Linux, but then there are versions that will run on Windows and the Mac also. And it's a hybrid of C++ and Python, and has a kind of a flow graph abstraction, and runs on top of most of the commonly used computational libraries out there. Typically has a flow graph architecture like this. Basically, there are multiple sources, multiple processing blocks, and multiple sinks which can be interconnected to create a sample stream that will go from the source all the way to the sink. And then you can write this abstraction as a flow graph in Python. Or there is a similar variant that you can write in C, and then you can start it and the radio processing goes on. There are a wide array of modules that are available. If you're interested, you can try taking it up. You can build a lot of interesting projects on GNU Radio. There's also a GUI kind of an application which will give you a Simulink kind of an interface where you can interconnect blocks, build a flow graph, and then write the equivalent Python code. And it's very functional and very good for people who are interested. This would be the typical kind of application that the front end that you will see in GNU Radio. There's also a wide array of applications for common demodulation tasks that is available in this archive called the GNU Radio Archive Network. You can go there, and a lot of projects are present there which you can take and study and improve and use. So some of the functions that are available, I would skip these. And these are some of the open tools and softwares that are available. MATLAB and Simulink, I think you already know. LabVIEW is also another commercial platform that will allow you for doing most of these tasks. There are also these development frameworks called SOAP SDR, Photo SDR, and Liquid DSP that will allow you to do a lot of platform development, real-time processing, and development of these. There are also other function-specific software that is available, SDR++, SDR Sharp, SDR Angel. So these are radios these are software that are more or less locked to specific radios and would allow you to do a broad spectrum of modulation and demodulation applications. There is also a commercial upcoming software that is gaining a lot of popularity in the SIGINT space. And it's called the 3D Labs Scepter, which would do a lot of signal classification and signal detection and so on and so forth. So artificial intelligence is also making a lot of inroads into the software design in software-defined radios. So typically a lot of data banks are being constructed now using, so there are essentially test beds that are available from these companies called DeepSig, which allows you to capture and train neural nets from wide array of spectrum data and then use it for a lot of interesting constructive purposes, which was previously not known or not used. One of the preliminary applications they are essentially working on is to do spectral awareness and being able to detect what are the types of interferers, what is the kind of data that is getting transmitted. So essentially the basic idea is that you train a neural net on IQ data coming from different modulation schemes, and then you use that to predict unknown demodulations that is happening. So it can basically be used to figure out what is the kind of modulation that is happening, be able to detect what the source is, who is the interferer, what is the type of modulation scheme, what is the intelligence that is being transmitted, and so on and so forth. And a lot of development is happening in this area right now, where you can combine the advances in the machine learning space with that of radios and then use it constructively to build solutions in the signal intelligence part of the site. There is also developments that are happening in fine layer, which is very interesting. So basically the earlier radios essentially had an equalizer, a demodulator, a channel estimator, everything put on as a single block inside the radio. Now we can see that there is this development that has happened from DeepSig called Omnify. So essentially you have modulation data and demodulation data that is available across a wide spectrum of techniques, now all collected, and the machine learning tools are used to figure out, and then you have a single demodulator that can perform better channel estimation, better demodulation, do it in a more cost-effective manner, and combine this with the developments that we are doing earlier. So you have essentially antenna tower or an antenna, sector antenna, that essentially has all the RF sensing elements, the antennas, the front-end electronics, everything all coupled to a single RF sock. You feed it power, out comes a fiber, okay, which has all the IQ data, gigasamples wide, have it transported across to a server farm where your baseband radio runs as a virtualized server in some server farm, right? So that is a new change in architecture that is happening, and people are no more looking at localized tangible radios. Radios have become more intangible, and as a result there are a lot of developments that are happening in this field. I would definitely request you to kindly go and look at deepsig.ai and see the kind of work that they are doing there. And for those of you who are interested in pursuing this as a career, a lot of futuristic stuff is happening in this field. So that's the first half of the talk. The next portion I was actually planning to address to those typically in the undergraduate area. But I hope probably it might be exciting for some of you also as well. So typically, if you look at, if I'm a student who is looking forward to working in this industry, what should I learn? What are the topics that I should pay attention to in my curriculum, right? So typically, if you look at the software-defined radio architecture, you have these key topics that actually play a role, right? So there is antenna design and simulation that is involved, RF circuit design and simulations, RF measurements and instrumentation, power amplifier design, which is also part of the RF circuit design part, ADC and DAC architectures, computer architecture, embedded systems, signals and systems, digital signal processing, communication systems, and computer algorithms. These are to name a few of the topics where a lot of requirement is there for trained specialized engineers. Antenna design and simulation, I don't think I'll have to tell CUSAT about what is required, but typically a good theoretical and practical understanding of antennas, good understanding of software tools like ANSYS, HFSS, CST Microwave Studio, etc. A good background in computational electromagnetics is very welcome, and a good understanding of antenna measurements, radiation pattern measurements, return loss measurements, and so on and so forth. A good amount of experience is required on antennas, because antennas are actively becoming a part of the radio. And also another important requirement these days is the expertise in doing phased array antenna design, especially with a lot of applications in SATCOM, 5G, radar, direction of arrival estimation, etc. And a good understanding of beamforming theory and algorithms, along with a good understanding of these tools like Keysight System View or MATLAB phased array toolbox is very much required, because almost all the new antennas are coming are phased array designs, and there is a lot of requirement in the industry for people with these expertise. RF circuit design and simulations, a good understanding of RF building blocks, essentially low noise amplifiers, filters, mixers, divider combiners, oscillators, circulators, terminations, etc. The applications of these with hands-on experience on how most of these can actually be used, right? A good understanding of RF measurements, S parameter measurements, how to use a network analyzer, how to de-embed, how to good command over a network analyzer, a spectrum analyzer, and a vector signal generator is a must. Good understanding of transmission line design, good understanding of the concepts of insertion loss, return loss, noise figure, 1 dB compression point, third-order receipts, etc. And a good requirement is there for people who know how to do power amplifier design, how to do stability analysis, harmonic analysis, stability analysis, matching circuit design, biasing circuit design, and so on and so forth. And the key tools that actually come into play are the Keysight design suite. We require people who have expertise in these softwares, and most of the time these days these are the leading software, and you require a lot of expertise in these fields. And if you are having these tools in your university, please take your time to tinker with it, build circuits with it, and see how they actually come by doing measurements. Another important skill that is required essentially is in PCB design and manufacturing, a good understanding of how to read a device datasheet, schematic creation, footprint creation, high-speed design and layout, controlled impedance PCB design, signal integrity tools, thermal design, design for manufacturing. Because these are mundane things, but a lot of requirement is there if you have to realize a hardware system. And I would urge you to how many of you have built a PCB before on your own? Raise of hands. That's what, 4%, 2%, 3%. I would urge you to go ahead and build a small circuit. Maybe it is a blinking LED, but at least figure out the entire processes that actually go between creating a circuit and taking it all the way out to a substrate. I think an electronics engineer should have some appreciation of that process, right? To have tinkered and soldered a circuit on your own and so on. And the main tools are essentially KiCad, Altium Designer, Cadence Allegro, and so on and so forth. And if you're interested, these are some of the PCB manufacturers in India: PCB Power, Micropack, HiQ, PC Process. And there is good component assembly facility available in Maker Village, Kalamashiri, Kochi. So I urge you to at least go ahead, think of a circuit, build a printed circuit, get it manufactured, solder components onto it, get it to work. Okay, that is I think that is a bare minimum thing that one should be able to do as an engineer in this field, right? Then key understanding of ADC and DAC sizing is another required skill. essentially good understanding of A to D converters and D to A converter architectures, ADC resolution, sample rate, signal to noise ratio, ENOB, total harmonic distortion, integral and differential nonlinearities, porphyry dynamic range, quantization noise, etc. Good understanding of these concepts. How to size an A to D converter for a given job, for a given signal to noise ratio constraint, and so on and so forth. You need to understand. And good understanding of the ADC and DAC interfacing standards, and also how to do good input matching for RF ADCs, and good understanding of transmission line theory and number representation formats, etc. And I would urge you to take a look at data converters from analog devices and Texas Instruments. There's a broad spectrum of converters that are available. Try to understand their specs, try to understand how they actually are used for different applications, what are so special about them, try to understand their architectures. It's a very important. So mixed signal design is a key concept that people need to take in if you're looking into enter into any of these disciplines. Embedded systems, I'm sure almost all of you will know. Good expertise of field programmable gate arrays, system on chips, the Vivado and Vitis platforms if you're planning to work on the Xilinx SoCs, TI DSPs. These are some of the platforms that we would urge you to figure out and build an expertise in if you are planning to work on embedded systems. Good understanding of signals and systems is another requirement. Quite interdisciplinary if you look at it. And a good understanding of the LTI systems, convolution, impulse response, FIR filter, IR filter, Fourier transforms, quantization effects in time and amplitude, fixed point number representation. All these areas are important if you are planning to build radios on software-defined radio platforms. Then if it comes to communication systems, fundamentals like modulation techniques, single carrier modulation schemes, OFDM, equalization, channel estimation, that sort of stuff, primarily based on MATLAB. And then if you are interested in going in radars, these are areas which you probably might try to consider looking at. If not all of these, okay, I would urge you to pay close attention. This was specifically meant for BTechs. I'm not sure how much relevant it is for MTechs, but still be able to understand the basics of Ohm's law, Kirchhoff's law, Thevenin and Norton's theorem, network analysis, electronic devices, linear integrated circuits, operational amplifiers, and so on. Basics of signals and systems, sampling theorem, aliasing, filter design, Fourier analysis, antennas and wave propagation. The sad thing is, the reason why I'm putting this slide is during the COVID pandemic, we did an interview where we interviewed around 400 candidates. Some of them were BTechs, some of them were MTechs, some of them had long industrial experience, 3-4 years. And we used to start our interviews with very, deeper questions, essentially on spectrum analysis, wavelet decompositions, and so on and so forth. And I learned my lesson that these days I begin my interviews with one question. I draw a potential divider, that is, I draw two resistors in series, and I ask them the voltage division formula. Okay, so the top resistor is R1 and the second resistor is R2, and input voltage is V in. I ask them what is the formula for V out. The answer comes V out is equal to V in into R1 by R1 plus R2, R1 being the top resistor and R2 being the second resistor. So I ask them, do you think the answer is correct? And they are confident, they are more confident than the interviewer. So I tell them that, see, in my understanding it is V in into R2 divided by R1 plus R2. So could you go ahead and derive this from first principles? Can you apply Ohm's law and try to do this? And invariably, they draw the two resistors and mark currents I1 and I2 in the two resistors, right? Two resistors connected in series. So I ask them, see, should there be an I1 and I2? And they say, sir, yes, you require two currents. There are two resistors, therefore you require two currents, right? So I fold my hands in prayer to them and I tell them that, my dear friend, during your tenure as an undergraduate student, you should have solved typically around hundreds of Ohm's law problems, if not thousands, right? If I cannot have basic understanding of Ohm's law, I cannot make him do design, do whatever you do, right? So all the topics that I mentioned before are all fine, but if you don't understand these, then nothing can be built on top of that. So while you are students, while you are in the university, you've got a lot of time, a lot of resources, a lot of free space to think in your mind. Learn your fundas here. Please don't waste your time. Your time in your university is the most beautiful, precious time that you're going to get. Spend time in your laboratories and your libraries, figure out, learn, and pay very close attention to fundamentals. Very close attention. All the other things, higher skills can always be built once your fundamentals are strong. I might sound like a cliche, but it's very important, and it cannot be, no matter how much I tell these, I find that to be important. And these are some of the free advice to a younger self. Be a jack of all trades and a master of one or two. Okay, so I had listed a lot of areas for you to follow. At least have a good understanding of systems engineering, and that's very important if you're planning to do a career in electronics, or for that matter, any engineering. You should be able to understand how complex systems can be broken down into simpler systems, and how these simple systems interconnect, intercommunicate, and interoperate to build a bigger whole. And that understanding is key and crucial for you becoming a good engineer. So pay close attention to bordering subjects also while you are spending time specializing in one area or two areas for that matter. Okay, that's very important, and I cannot overstress this particular topic. Second thing is, I would like to inspire you all to have a toy project outside of what is taught in the curriculum, right? Go out and build some electronics on your own, not because your grades matter, but because you are an engineer, right? Go out into the market, buy components, okay? Because I remember when I was an undergraduate, my first project was basically, one of my friends had that poultry farm, and he wanted to build a thermometer so that he could read out temperature and maintain the right temperature using a control system. So in my college, we didn't have permission to do most of these things. So I remember in the nights we used to, get up and had a breadboard, and we didn't know how to read a data sheet. And we had an A to D converter, and, didn't know anything about it back then. And then tinkered and figured a way out, and actually could read out temperatures from an LM35 IC. And that experience I'm still even using to this day in my career, right? It is important to have toy projects. I have always had a toy project right from the time I was in my undergraduate degree to my present day. I tinker with stuff, and it is very important. And most of these things that you learn outside or come to practice is always come to bear on the toy projects that you have. I would strongly urge you to build some electronics on your own. And more importantly, engineering is practice. You have to do internships, go out, get apprenticed, and work on an apprenticeship. And that's very important, because unless you have exposure, unless you have hands-on, most of these things will always remain in textbooks. And it will always inspire you to take up your class material more efficiently. I would also urge you to learn one programming language well. It can be C, C++, Python, any of those. But it is important to have programming as one of the tool sets in your arsenal. And I would again overemphasize strong foundations and fundamentals. Thank you. And to give you a brief of what we do, I'm from this startup which I co-founded with my brother. The company is called Asnaviram Networks, and we basically work on RF embedded systems, FPGAs, Zinc SoCs, RF SoCs, mixed signal front ends, DSPs, ARM processors. And we have good amount of interest in doing RF systems, signal processing systems, embedded electronics manufacturing, and so on. And we have our core focus areas as software defined radios and phased array systems, with applications in SATCOM, signal intelligence, electronic warfare, radar, defense applications, etc. And I would like to say that there are a limited number of internships available. Those of you who would like to get your hands dirty are welcome, and you could send your resume to me at ajith@asnaviram.in, and we would like to be interested to work with some of you if you are interested. I would thank you, and I would welcome any questions or any topics of discussion that you might have. Okay. I hope I'm not taking too much time, but I'll just quickly So basically, GNU radio essentially is a flow graph based software defined radio platform, and the basic idea is that you have, so if you took a radio, essentially the baseband implementation of a radio, there are essentially blocks. Okay, there is often some kind of a signal source from where samples come in, I and Q. I hope you understand by now that what I and Q is. And then it comes out, and there are a lot of applications that you normally perform. You have filters that you want to do. Probably there are visualization that you would like to do. There is signal processing that you would like to do, modulation, demodulation, etc. So for all of these are available as pre-programmed blocks or modules. And GNU radio essentially is a signal flow manager, essentially. What it does is it provides efficient scheduling systems like this, essentially. So basically you have blocks that are interconnected with each other through buffers. And what happens is samples are aligned and are converted, moved from block to block. Each block runs in its own thread. So all the operations that you need to run a flow graph are abstracted out from you, and you have to put all your attention in writing individual blocks, and data flow between them is scheduled by a scheduler. And it's a very robust architecture, and it allows you to do a wide array of data types and allows you to do almost all the functions that you can think of. And you can also write your own modules in Python or C++, and you can attach it to the flow graph. And if you have used Simulink or LabVIEW, the architecture is very similar if you look at it from the outside, but there are big differences also in the way the software is architected. And a lot of even professional softwares use GNU radio as a backend to manage signal flow between them. Okay, a more detailed discussion would be due in the sense that, if you have to look at the architectures and so on and so forth, it will require a bigger session to present the ideas. Yes. Yeah.
My first question is that the major challenging part of this SDR radio hardware design is interference from the digital chips.
Yes.
to the RF front end.
Yes.
Especially in frequencies below 30 megahertz.
Yes.
Which is commonly used in hardware for the ham radio.
Yes.
Okay, how to address that problem? And my second question is it have the same sensitivity and the selectivity as the same as analog radios?
To answer your first question, I am a radio amateur myself. My call sign is VO3MX. I significantly have problems in low frequency. And forget the problems that is arising out of the digital processing part. The biggest problems are these.
Okay,
the LED lamps. The LED lamps, right? You turn them on and you listen to somewhere in 5 meg or 7 meg or 10 meg for that matter. Your entire spectrum is gone, right? So if you really ask me, if you look at the proper design practices that are followed, so for instance, if you Faraday cage your electronics properly, if you design your transmission lines properly, if you put good filters into the design, all of these EMI sources can be mitigated to a great extent. It basically depends on how you design your circuitry. That is number one. And the noise that is coming out of your digital processors are the least of the problems if you are looking at sub 30 megahertz operation these days, right? We extensively do communication networks in Lakshadweep Islands, and nowadays we can't, basically because the entire band is crowded with noise that is coming in from UPS, from the LED lights, and from other switching mode power supplies that are around. So typically they operate in the 2.2 meg, but then the harmonics come all the way into higher bands also as well.
I think it's an improper design of filter circuit. In the case of cheap LEDs, there is no EMI filter.
There is no EMI filter, and these things basically come out of China, so you can't do any enforcement of anything, and the entire sub 30 megahertz band is gone, more or less, practically, if you ask me. People are using magnetic loop antennas to combat some of these interferences, but I'm not sure how they will actually pan out for wideband solutions as well also.
I think that proper shielding and filtering technique can improve the reception.
It can improve the reception, but then, when these antenna, the sources become so ubiquitous, it is almost hard to think of a solution. And I'm sorry, can you repeat your second question?
Second question is it have same sensitivity and the selectivity as analog receivers, all type of?
Depends on how you design. Depends on how you build your. There are radios like this AirSpy, if you really ask. Okay, these are essentially low frequency radios, and they are reported to have much better fidelity, selectivity, sensitivity than, typically we were, so one of the solutions when this Arikomban came out, right? So we had actually built a radio for the Kerala Forest Department, basically using an air spy. And because you have to find an elephant in deep forest, the sensitivity figures are required much lower. We had sensitivity figures, if I remember correct, at minus 140 dBm on VHF bands, which in my opinion is pretty reasonably good. If you took a, so there are radios that are available which have good sensitivity figures, and also depends on how you design your front end, how good you design your low noise electronics to be, how good you design. So it almost boils down to a design problem. If you know your figures, you can engineer them and you can correct them for better sensitivity and selectivity for that.
Okay, thanks for clarity.
Thank you.
Sir, is it possible to apply LoRa technology in the SDR?
I'm sorry?
LoRa technology.
See, LoRa SDR implementations are available. That is basically, these are essentially chirp modulation schemes that are available. There are open source implementations of some of the LoRa schemes already available in SDRs. You can check out in GNU Radio. I'm sure there is a LoRa implementation that is available in GNU Radio, which you can use to demodulate most of these IoT kind of applications. Yes.
Like, what are the thoughts on it? Is it is it a field to improve the traditional?
See, LoRa essentially is a chip-based modulation scheme. So there is good robustness that is available in the physical layer, but again, the throughputs are comparably low if you compare it to OFDM-based systems. So, and I think more or less the field is more or less dominated by Semtech, which is a company that is doing the product development, the ICs and other things. So I really don't know how much of improvements are there, but there are always avenues to look further, do deeper study of things and so on and so forth. But I'm sure most of it, I think, is almost a cracked problem. But probably I think there is a lot of applications that can come in the application side of it, where you apply LoRa to, and do a lot of developments in the application side of things. But I think the physical layer, I think, is probably more or less tight in my understanding. Probably I'm wrong, but yeah.
Thank you, sir.
Thank you.
Thank you, sir. We are now delighted to invite Professor Abdullah P. to present a token of appreciation to Sri Ajith Peter for his insightful contribution to today's session. Professor Abdullah, please join us on seats.